Hello, and welcome to the Math Club, Episode 2, Triple Play. I'm Noah King, an elementary school teacher who loves math.
And I'm Pete Littig, a software engineer, former math professor who loves math as well.
This is only our second episode. If you just stumbled across us now, you may want to go back and look for our first episode, which was all about zero. If you heard that episode and you are back for more, welcome back and thanks for joining us.
Yeah, definitely. We're glad you're with us. And in fact, we'd love to hear from you. Our Twitter handle is @MathClubPodcast, and you can email us at mathclubpodcast@gmail.com.
So, Pete, in thinking about today's episode, I was looking at an interesting video on YouTube yesterday. It was demonstrating the Pythagorean theorem. In all of your time getting a PhD in math, have you ever heard of the Pythagorean theorem?
I have no idea what you're talking about. Yeah, of course I have. And in fact, I bet everyone who's gone through high school geometry can tell you what the Pythagorean theorem says.
Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
No, Scarecrow, no.
Wow, he pretty much got every single part of that wrong, didn't he?
Okay, all right. Well, why don't we tell listeners what the theorem says, just to make sure we're all on the same page.
So if I have a right triangle, meaning it's got a right angle in it, that there's a relationship between the lengths of the sides. Often people say a squared plus b squared equals c squared. Right, where c is the length of the hypotenuse.
Exactly. What that means is if you take the square of one of the legs that's not the hypotenuse and add it to the square of the other leg that's not the hypotenuse, the sum will be the square of the hypotenuse. And so this video was a very clever visual demonstration of what this means. And I'd like to try to describe to you what it showed. So the person had taken a wheel and mounted it vertically so that it could be spun, kind of like the big wheel on Price is Right. But instead of looking at it edge on, you'd be looking at the circular side of it, and you could spin it either clockwise or counterclockwise. Does that make sense?
Yeah, I'm also sort of picturing in my head the face of a clock.
Right, exactly.
Yeah.
So it's oriented like the face of a clock, but it doesn't have hands on it. Instead, the person drew a right triangle right in the middle of the wheel, so that if you spun it, the triangle would be kind of spinning around its, more or less around its center. Then what they did was to each side of the triangle, they attached a clear plastic square box whose side lengths matched the length of that side. So for example, if the hypotenuse were 5 inches long, then they took a clear plastic box that was 5 inches on each side, and they attached it to the wheel so that one side of the square was exactly lined up with the hypotenuse.
Oh, I can picture this. I've seen diagrams that look like this in geometry books.
Sure. And they did the same thing with the other two legs also. So what you end up with is a triangle, but each side of the triangle looks like it has a square kind of built off of it. And the side lengths of that square are the side length of that side of the triangle.
Got it. And the whole thing would spin in unison. Everything
spins together. And then what they did was they filled the two boxes that were attached, not to the hypotenuse, that were attached to the two legs. Those got filled with colored water. But all three of these boxes were positioned in such a way that water could flow between them if you turn the wheel in the right way. So what you ended up with was enough water in these boxes so that it filled basically the a square and the b square, but the c square, the one that was attached to the hypotenuse, was empty. When they rotated the wheel 180 degrees, so the hypotenuse was now at the bottom, water started flowing from the other two squares into the hypotenuse's square, into the c square. And the fascinating thing was you can watch and see that the exact amount of water in the a square plus the water in the b square exactly filled the c square. So a squared plus b squared equals c squared.
That's very cool. I would love to see that video. It sounds exactly like the kind of thing you want to show people when they're learning about the Pythagorean theorem.
Right. Well, we can put a link to that video in our show notes so that listeners can find it and take a look at it if they want.
Okay, cool. And, I was thinking, you mentioned a 5-inch hypotenuse, which of course comes from one of my favorite right triangles, the 3-4-5 triangle. very famous Pythagorean triple. So there would be a 3-inch base, a 4-inch leg, and then a 5-inch hypotenuse. And I think that's probably the first Pythagorean triple that most people learn about.
Well, I'm going to take your word for it, but I need to back up and ask you a question because you're mentioning this term Pythagorean triples, and I'm not sure that I've heard of those before.
Sure. Okay. Yeah. Sorry. Well, we know that if you have a right triangle, the lengths of the legs squared and added together give you the length of the hypotenuse squared. And that's true regardless of what size or scale this triangle is drawn at. There could be crazy lengths involved. One leg could be the square root of 3, and the other leg could be sine of, pi over 12. And this relationship would still hold. However, those numbers are hard to think about. It turns out that there are some very familiar numbers, like 3, 4, 5, that describe a right triangle. Another example is 5, 12, 13. So what these illustrate is a Pythagorean triple, which consists of 3 positive integers whose values satisfy a squared plus b squared equals c squared. So
when you're talking about Pythagorean triples, you're just talking about different sets of right triangle lengths, where the lengths are all whole numbers, and
yes, that's exactly it.
Not fractional parts or irrational numbers.
Yeah. And these are the ones that students and other people remember because they're whole numbers. And 3, 4, 5 is a very friendly combination of whole numbers.
Interesting. Obviously, I've heard of a 3, 4, 5 triangle because I think it's the standard example that everybody learns about in geometry. I had not heard about the 5, 12, 13 triangle. How many Pythagorean triples are there?
Well, it turns out there are infinitely many of them. Other examples, just to get them out there so we have something to talk about: 8, 15, 17, 20, 21, 29, 12, 35, 37, and so on. And in each of these cases, for example, 12, 35, 37, the relationship 12 squared plus 35 squared equals 37 squared. That's a true relation. And people have been fascinated with these whole number triples for quite some time, many thousands of years, actually.
Well, when you say people have been interested in these for thousands of years, it makes me wonder, does this go all the way back to Pythagoras and when the Pythagorean theorem was originally discovered?
It surprisingly goes back quite a bit before the time of Pythagoras. Pythagoras, it's thought, lived from somewhere around 570 BCE until 490 BCE. So that's roughly 2,500 years ago. Well, there was a Babylonian clay tablet named Plimpton 322, and it contains on it a list of 15 Pythagorean triples, what we now call Pythagorean triples. And it is thought to be roughly 3,800 years old. So that is a good 1,000+ years before the time of Pythagoras.
So wait a minute. How is it possible that people were finding these Pythagorean triples before Pythagoras even came up with the Pythagorean theorem?
That's a good question. And I think there's some confusion in the world about who discovered and who first proved the Pythagorean theorem. It turns out we have no evidence that it was Pythagoras himself.
What a credit stealer.
Well, he may not be the guilty party here. So a couple of hundred years after Pythagoras, another famous Greek mathematician, Euclid, wrote a sequence of books called The Elements. Very famous, right? And in the first of those books, he presents theorem number 47, the Pythagorean theorem. He doesn't call it that, but it is that theorem that states the relationship between the legs and the hypotenuse of a right triangle. Some hundreds of years later, the Greek commentator Proclus, in summarizing Euclid's work, referred to that theorem as the Pythagorean theorem. So, beyond that sort of hearsay, we don't know that Pythagoras is the one who discovered the theorem. We don't know that Pythagoras is the one who proved the theorem. All we know is that his name is attached to it.
Could we go so far as to say that we know he was not the first person to work with this theorem, since there's a clay tablet some 1,300 years prior to him that shows these triples?
It may have been the case that the Babylonians noticed that if you used various combinations of these integers, these whole numbers, that you could create right triangles. They may not have gone so far as to know that any right triangle satisfies this a squared plus b squared equals c squared relationship.
They may not have even noticed that relationship between these lengths. They may have just been writing down lists of numbers that they could make right triangles out of and not even noticed the relationship of the squares of the sides.
Yes, that is entirely true as well. I think there's a world of exploration in this tablet, Plimpton 322, and I would definitely encourage listeners to go track it down, take a look at it. It's a wonderful historical artifact showing early understandings of mathematics.
So that's really interesting. And I'm fascinated by the idea that for thousands of years at least, people have been looking for these triples that can be used to define right triangles. Why are they so interesting to find? Why do people like looking for these?
You know, there are probably many reasons, some of which are deeply embedded in mathematical practice. There's a connection, for example, between Pythagorean triples and Fermat's last theorem, which is undoubtedly one of the most famous theorems of the last, say, 300 or 400 years.
So famous, I've never heard of it. But of course, I don't have a PhD in math like you do. I've taught math up to 5th grade.
Well,
we didn't get into Fermat's last theorem. We stopped at like his 3rd or 4th theorem.
Well, I think you and I should do an episode later about Fermat's last theorem. But I will say this. Andrew Wiles, currently living mathematician, the one who proved Fermat's last theorem in the mid-90s, became interested in Fermat's last theorem at age 10. And that certainly predates 5th grade. So I think it's fascinating that a 5th grader or a 4th grader could be interested in this. And that brings me to another answer to your question. Why are people drawn to this? There's just something about a set of numbers staring at you with some pattern, and your mind wants to know, are there others? Can I find more of these? And so it wasn't just 1,000 or 2,000 or 4,000 years ago that people looked for them. I looked for some last night. And can I tell you actually how I went about finding some of these?
Yeah. So you mean you didn't just go and look up Pythagorean triples? You were trying to see if you could find a way to generate them?
That's right. You know, I know some of these off the top of my head. I don't know a ton of them, but two that I know, we've already mentioned them, 3, 4, 5, 5, 12, 13. Something stands out about these two, and it's more evident in the second example. But if I think of these as labeled A, B, C, so 3, 4, 5, A is 3, B is 4, C is 5. Notice in both examples, C is 1 more than B. 5 is 1 more than 4. 13 is 1 more than 12.
Gotcha.
Exactly.
Okay.
So I thought maybe there are other Pythagorean triples that have this property where C is equal to B plus 1.
Okay.
Well, if you take the equation A squared plus B squared equals C squared, and you replace C with B plus 1 in that equation, and then do some algebra, you find that actually B depends on A as well. So not only is C 1 greater than B, there's a dependency there, right? C depends on B now, but B depends on A. Namely, B is equal to A squared minus 1 divided by 2. Well, if C depends on B and B depends on A, that means C also depends on A. So our triple that we started with, ABC, can be re-expressed entirely in terms of the number A.
That's interesting. Is this true of all Pythagorean triples or just the ones where C is 1 more than B?
Not all of them. It's just the ones where C is 1 more than B. And if you apply this reduction so that you reduce everything to depending on A, I wrote down, well, here are the examples I found. 3, 4, 5, 5, 12, 13. We've already mentioned those. Here's the next one. 7, 24, 25. And the one after that is 9, 40, 41. This list is infinite, and not only is it infinite, and no two of them are the same, but there's also something interesting between the three numbers that appear in these triples.
What's that?
They have no factors in common. So 9, 40, and 41, there is no number that will divide equally into 9, 40, and 41.
They don't have any common factors.
They have no common factors. And those are sort of the most special of the Pythagorean triples, and they're called primitive. But that's not all the primitive ones. There are more. And it requires a little more work to find the other ones. But if you make certain algebraic observations between the quantities A, B, and C, sure enough, you can come up with a formula. Well, there is a formula, and it is now known as Euclid's formula.
I want to interrupt for a second, make sure I understand something you said. So 3, 4, 5, you would say, is a primitive Pythagorean triple because there are no factors that divide into 3, 4, and 5.
That's right.
So I believe also 6, 8, and 10 is another Pythagorean triple.
Ah, you're right.
But just to make sure I'm understanding this right, so 6, 8, and 10 are not what we would call coprime, which means they do have a common factor, namely 2. You can divide 6 by 2, 8 by 2, and 10 by 2. In fact, if you divide 6, 8, and 10 by 2, it brings you back down to 3, 4, 5.
Exactly. This is very simple.
Is that where we would say 3, 4, 5 is the primitive triple and 6, 8, 10 is sort of a, for lack of my having better terminology, is a multiple of that triple?
Yeah, that's exactly right. And in fact, we can draw a comparison to the reduction of fractions into lowest terms. So if I give you a fraction 6 over 8, you're going to say, oh, you mean 3 over 4? And what you have done is you have noticed that 6 and 8 are not coprime. They're not relatively prime. And you have factored out the common term to reduce it to 3 over 4. This is exactly the same thing that we want to do with Pythagorean triples. That's the preferred way to look at it. And then there's a whole family of multiples. So 6, 8, 10, 9, 12, 15, and so forth. So those are the ones we really care about. They're the ones that are the most fundamental.
Is it going to necessarily be true that if I take a primitive triple like 3, 4, 5 and multiply all 3 of those sides by the same number, I will get another Pythagorean triple? Or did that only coincidentally work when I multiplied them all by 2?
It will work as long as you multiply by a whole number.
So if I take 3, 4, 5 and I multiply all of them by 5 and I get 15, 20, 25, that will be another Pythagorean triple?
It will. And multiplying by 5 has a geometric interpretation, which is to say you've blown the image up. You've got an image of a triangle whose side lengths are 3, 4, 5, and then you magnify it by a factor of 5. You've just
I'm making a similar triangle that's bigger.
Exactly. That's exactly right. Now, I could take that 3, 4, 5 triple and multiply it by a half. So now I've got 3 halves, 2, 5 halves. Not a Pythagorean triple because we don't have whole numbers.
Right.
However, those 3 numbers do describe a right triangle.
Interesting.
This makes me think of some unexpected but also very cool connection between Pythagorean triples and the unit circle.
Okay, but before you go on, I just want to make sure all of our listeners understand what you mean by the unit circle. That would be a circle where the center of the circle is at point 0, 0 on the graph, and that the circle itself intersects the x and y axes at 1 and -1. Is that right?
Yes. So the circle has the origin as its center point, and its radius is 1.
Gotcha.
So rather than taking a primitive triple and expanding it out, let's pick a primitive triple, and I want to shrink it down until the hypotenuse becomes a side of length 1. So this triangle now will live inside the unit circle, and its hypotenuse will extend from the origin out to a point on the unit circle. Does that make sense, that picture?
Yes.
So if we start with a primitive Pythagorean triple and we shrink it this way, like let's take 3, 4, 5, for example. I want to shrink this so that its hypotenuse has a length of 1. Well, that I can achieve that by dividing each coordinate by 5. So now my triple becomes 3/5, 4/5, 1. And because the hypotenuse has length 1, this little triangle will sit inside the unit circle and have a radius as its hypotenuse. But here's what's cool. That describes a point on the unit circle whose coordinates are rational numbers. If I were to have turned this around and said, hey, Noah, do you know any points on the unit circle that have rational coordinates? What would you come up with? What would you tell me?
First I would open my web browser and I would type that question in.
No, you wouldn't. You don't have a web browser. It's just you.
I don't know. I don't know what I would tell you. Uh,
It seems hard, right?
I'm not sure how I would figure that out.
And part of why it seems hard is that most students who have studied trigonometry will start messing with sine and cosine because they know that a point on the unit circle has cosine of an angle for its x coordinate and sine of an angle for its y coordinate. But the question of how do you get cosine and sine, those functions, to simultaneously produce rational outputs, that is a hard question. But we have this new tool. Any primitive Pythagorean triple can be shrunk this way, making the c value, the third coordinate, equal to 1. Its other two coordinates will be rational numbers necessarily because all the starting points were integers. And this will produce a rational point on the unit circle. And in fact, every primitive Pythagorean triple will produce such a rational point. And in fact, every rational point could in turn, by magnification or blow up, produce a primitive Pythagorean triple.
And how is this process useful?
Well, it's useful in that there are several branches of mathematics, number theory and algebraic geometry in particular, that are very interested in finding rational points on geometric structures. So,
and this is kind of an easy shortcut for doing that with the unit circle.
With the unit circle. And of course, this is just the tip of the iceberg. An algebraic geometer would have a handbag of examples and be able to talk not just about rational points in this sense, i.e. like fractional coordinates, but they would extend this into arbitrary dimensions, and they would be working with number systems much more exotic than the ones that we're discussing here. But I love that something as sort of humble and familiar as a Pythagorean triple, just think 3, 4, 5, is related to, and in fact is the tip of a very large iceberg. And that's part of the magic of mathematics, that oftentimes we look at the horizon and we see these little iceberg tips pointing out in the ocean, and underneath are these vast worlds to explore, the rest of the iceberg, if you will. Will you?
I will.
Okay. Well, I think that is probably enough for our first foray into Pythagorean triples.
Yeah, I agree with you. Although I am intrigued. We're not going to get into it now, but I am intrigued now by Fermat's last theorem, which you alluded to earlier, was an interesting step to go into from here.
Oh, yes. It's a fascinating story. I'm really looking forward to taking it on. And for listeners who are interested in Pythagorean triples, there's a really lovely video by a YouTuber named 3 Blue 1 Brown. And I would highly recommend that listeners take a look at that video, in addition to the spinning wheel that you described at the top of the podcast.
We'll put links to both videos in our show notes so that people can find them easily.
That sounds great. And hey, we'd love to hear from you. Our email address is mathclubpodcast@gmail.com. And our Twitter handle is @mathclubpodcast.
Do you think also Pythagoras' favorite sandwich at Togo's was probably the triple dip?
I have no idea, but I personally love a good French dip.
Pythagoras wasn't French, though, and I don't think there is such a sandwich as the Greek dip.
There ought to be if there isn't. Well, on that sandwichy note, I bid you adieu from the Pacific Northwest.
And I don't know how to say goodbye in Greek, so I'm just going to say signing off from the Bay Area. Thanks for joining us, and we hope to see you next time.
Indeed.